All right, welcome linear algebra students. So let's take a look at a 3 by 3 matrix A where we want to find the characteristic equation and solve the characteristic equation associated to this matrix so we can identify the eigenvalues of this matrix. So in this case, we have a 3 by 3 matrix, so we should expect that the characteristic polynomial is going to have a degree 3, and we may have at most 3 different eigenvalues for this matrix. So recall that the characteristic polynomial that we can set up first, we get by looking at the determinant of the matrix A minus lambda I. So in this case, our matrix A is a 3 by 3 matrix where the first column is 1, 0, 1. The second column is 2, minus 5, 8. And the third column is 1, 0, 1. So when we look at the matrix A minus lambda I, this means that we are subtracting lambda from the diagonal entries of matrix A, and we're not doing anything to the off-diagonal matrix entries of matrix A. So the matrix A minus lambda I would have a first column which is 1 minus lambda, 0, 1. The second column would be 2, and then for the diagonal entry, it's minus 5 minus lambda, and then 8. And then the last column is 1, 0, and now we have the last diagonal entry is 1 minus lambda. And we want to calculate the determinant of this matrix. And so if we look at the matrix that we have, it seems like doing a cofactor expansion across the second row will actually be a pretty efficient way of finding this determinant because this row has 2 zeros in it. So using a cofactor expansion across row 2, we would get 0 times the determinant of the submatrix that we get over here, which is going to be 0 times whatever that is, we'll get 0. And then from this entry, it is in the 2, 2 position in this matrix. So that means we don't have to have a negative sign out in front. For entries that have indices that add up to an even number, we would just have the entry minus 5 minus lambda, and then we're going to multiply by the determinant of the submatrix that we get when we remove the second row and the second column. So that gives us a resulting submatrix that has the first column 1 minus lambda 1, and second column is 1, 1 minus lambda. So now we can calculate the determinant of that 2 by 2 matrix. So we have this leading minus 5 minus lambda, and I just factored out a negative sign from both of those terms. So we can write this as negative 1 times 5 plus lambda. And then to calculate the determinant of this 2 by 2 matrix, we would take the product of the diagonal entries, which gives us 1 minus lambda squared, and then we subtract the product of the off-diagonal entries, which is 1 in this case. So now I've got minus 1 times 5 plus lambda, all times 1 minus lambda squared minus 1. So let's group our terms together here. So we're going to simplify the expression that we get when we compute the determinant of the submatrix. So we would get 1 squared minus 2 lambda plus lambda squared, and then we subtract 1. So the constant that we get when we expand this expression is going to cancel the 1 that we have when we took the product of the off-diagonal entries. So I've got a negative 1 times 5 plus lambda, and this expression simplifies to lambda squared minus 2 lambda. So here we have our characteristic equation, or excuse me, this would be the characteristic polynomial because we don't have anything on the right side of this equation yet. And it doesn't make sense for me to distribute these terms here because if we want to figure out when is this expression equal to 0, it's actually more convenient to have this in a factored form. So I can pull out a lambda from this quadratic term, and this polynomial just looks like minus lambda times 5 plus lambda times lambda minus 2. So we have 3 factors for this cubic polynomial, so we should expect from each of these factors we get a different eigenvalue for the matrix A. And so setting up the characteristic equation would therefore be minus 5 plus lambda times lambda squared minus 2 lambda equals 0. And then we can factor that and identify the zeros, which would be lambda is equal to minus 5, 0, and 2. So these 3 values, minus 5, 0, and 2, represent the 3 eigenvalues for our matrix A.